This is a video from section 11.1. The directions say to determine whether the sequence a sub n converges. If a sub n converges, we want to find the limit. So in example 1, we have a sub n equals 3 plus 5n squared divided by 1 plus n. Now, the highest degree in the numerator is 2. So we want to factor out an n squared. When I do that, I'm going to take 3 and I'm going to divide by n squared and I'm going to add 5. In the denominator, the highest degree is 1. So I'm going to factor out the n, and then I'm going to take every term and divide by n. So I get 1 over n plus 1. So therefore, a sub n is n times 3 over n squared plus 5 divided by 1 over n plus 1. So therefore, I'm going to take the limit as n goes to infinity of a sub n. This is the limit as n goes to infinity of n times 3 over n squared plus 5 divided by 1 over n plus 1. Now, as n goes to infinity, 1 over n is going to go to 0. And as n goes to infinity, 3 over n squared is also going to 0. And so what we have left is infinity. And so therefore, the sequence a sub n diverges. So this is just another example of a sequence that's going to diverge. Okay? That's example 1. Let's take a look at example 2. Suppose a sub n is 2 plus 0.86 raised to the nth power. Now, the absolute value of r is 0.86, which is less than 1. Therefore, if I take the limit as n goes to infinity of 0.86 to the nth power, that's equal to 0. Okay? Therefore, if I take the limit as n goes to infinity of a sub n, this is the limit as n goes to infinity of 2 plus 0.86 to the nth power, which is equal to 2 plus 0, which is equal to 2. And so what that implies is that the sequence a sub n converges to 2. Let's take a look at example 3. Suppose a sub n is 4 to the n divided by 1 plus 9 to the n. Okay? Now, I'm going to take a look at the absolute value of a sub n. But this is the absolute value of 4 to the n over 1 plus 9 to the n, right? But the terms inside the absolute value bars are non-negative, which means we can write this as 4 to the n over 1 plus 9 to the n. If I make, so let's pay attention to this denominator. If I make the denominator smaller and leave the numerator alone, the overall value gets bigger, right? So in other words, I can say that this is less than or equal to 4 to the n over 9 to the n, which is 4/9 to the n. Okay? Now, by the way, the absolute value of a sub n is also greater than or equal to 0. I need that. Okay? Now, the limit as n goes to infinity of 4/9 to the n equals 0. And so, by comparison, so we can say, let's try that again. We can say the limit as n goes to infinity of the absolute value of a sub n is 0 by comparison. Okay? Now, if the limit as n goes to infinity of the absolute value of a sub n equals 0, then the limit as n goes to infinity of a sub n must also equal 0. And that's a really, really nice way to demonstrate this result. Okay? Let's go ahead and take a look at this one. So we're going to call this example 4. So a sub n is cosine of n pi divided by n plus 1. Okay. Now, if I take the limit as n goes to infinity of n pi divided by n plus 1, that's the limit as n goes to infinity of n pi, that's in the numerator. In the denominator, I'm going to factor out the n, and in parentheses, I get 1 plus 1 over n. Notice how the n's cancel. And as n goes to infinity, 1 over n is going to go to 0, and then we're going to get pi on top. Now, I'm going to let f of x equal cosine x. Can we agree f is continuous at pi, right? And so, therefore, the limit as n goes to infinity of a sub n, that's the limit as n goes to infinity of cosine of n pi divided by n plus 1. Now, because f is continuous at pi, that's going to allow me to slide that limit in. So I'm going to take the limit as n goes to infinity of n pi divided by n plus 1. But that's cosine of pi, and cosine of pi is negative 1. And so, therefore, the sequence a sub n converges to negative 1. That's how we do example 4. Let's take a look at example 5. So, in example 5, we have the following. So I'm going to take an, that's the absolute value of negative 1 to the n plus 1 times n, divided by n plus the square root of n. Okay. Now, would you agree that I can strip away those absolute value bars, right? Because the absolute value of a negative number is a positive number. The absolute value of a positive number is still positive, okay? And so what we ultimately end up getting is n over n plus the square root of n. And so a sub n is n over, now I'm going to factor out an n from the denominator, and when I do that, I get 1 plus 1 over the square root of n, like so. Notice how the n's cancel. And we get 1 over 1 plus 1 over square root of n. So I'm going to take the limit as n goes to infinity of 1 over 1 plus 1 over root n, right? And as n gets big, this value is going to go to 0. And so this is equal to 1. And so we can say that this sequence a sub n must converge to 1. And I hope that's okay. All right, so let's do another example, and we're going to call this example, we'll call this example 6. And okay, so we're going to take a look at this one. A sub n is n squared divided by e to the n. And we want to know what's going on with that. Now, remember, we have to be careful. We can't apply L'Hopital's rule here. What we can do is let f of x equal x squared over e to the x. And then I'm going to take the limit as x goes to infinity of x squared over e to the x. Now, this is of the form infinity over infinity, right? So by L'Hopital's rule, and I'll label this LH for short, this is the limit as x goes to infinity of 2x over e to the x. Again, this is of the form infinity over infinity. So this is the limit as x goes to infinity of 2 over e to the x. And the limit as x goes to infinity of 2 over e to the x equals 0. And so, therefore, the limit as n goes to infinity of a sub n equals 0. And so what that tells me is that the sequence a sub n must converge to 0. And that's how that works. Now, with that, let's take a look at example 7. So here, I'm going to do a sub n equals we'll do the nth root of n, which is n to the 1 over n. Now, what's going on there? So a sub n is n to the 1 over n, which is e to the natural log of n to the 1 over n. But this is e to the 1 over n times the natural log of n. Okay, so I'm going to take the limit as n goes to infinity of natural log of n divided by n. Now, this is equal to 0, right? If we're not comfortable making that leap, you can apply L'Hopital's rule on the corresponding function, natural log of x over x. Now, but we do need to state this. F of x equals e to the x is continuous at 0. So the limit as n goes to infinity of a sub n is the limit as n goes to infinity of e to the 1 over n times the natural log of n, which is e to the limit as n goes to infinity of natural log of n divided by n, which is e to the 0, and that's equal to 1. It's very useful. And so, therefore, the limit as n goes to infinity of n to the 1 over n is 1. And so what that implies is n to the 1 over n must converge to 1. And I'm done. So that's probably a good stopping point for this video. This is a video on section 11.1, and we did 7 examples of finding a limit. So, or showing that a sequence converges or diverges. So, okay, thank you.